Now we will do some practice exercises for finding area, whether it's exact or approximating. Part A. Sketch the region between the graph of the function and the x-axis over the given interval. So here's our function. Over this interval, let's space it out so that we have a good visual. If we're only looking from 0 to 2, I'm going to mark this as 0, and perhaps every 4 blocks I'll put another unit. And this time up here, this is a parabola opening down. Vertex is up at 5, so let's count every 2 blocks being 1. That way we can put our vertex up here at 5, 0, 5. 1 unit over, it's going to be at 4. And 2 units over, 2 squared is 4. Negative 4 plus 5, that's 1. So that's right here where that ends. So here is the graph of the function on the interval from 0 to 2. Sketch the region between the graph of the function and the x-axis. So that region is from 0 to 2, the area between the curve we sketched and the x-axis. So we will shade in that region lightly right there. Okay, so there's that region between the curve and the x-axis. Done. Part B. Approximate the area of the region using 4 rectangles and right endpoints. So we know we have to split this region up into 4 subintervals using the right endpoints. So I'm going to cut in half, takes me here, and then cut in half again. Now if I'm not sure, can't visualize the half, then remember that the width of each rectangle, that's our delta x, that's b minus a over n. So b minus a is that length of the interval, 2 minus 0, or it's 2 units long divided by 4 rectangles, or each one is 1/2 long. So 1/2, and then 1, and then 3/2, and then 2, or 1.5. The first rectangle, this is the first width, the right side of it, go up to the function to find the height, and that is where we draw the height of the rectangle using right endpoints. So this is the first rectangle right here. Second subinterval on the right side, go up to the function and over, and that's our second rectangle right here. And then third rectangle, look on the right side, that's at x equals 3/2, go up to the function, go across. This is our third rectangle, and last rectangle on the right side, up to the function and across. And there's our last rectangle. So for this approximation, for part B, we're approximating the area with our right endpoints. And that means that we're finding the first area, its width times the height. Add it to the next one, width times the height. Third one, width times the height. And all of these widths are the same. So instead of having to say 1/2 each time, we're going to pull out the 1/2 factored out, and that's our width. Now we'll just add up all the heights. So our area is approximately equal to this estimation, the function value with the first x coordinate plugged in that we come to, plus the function value with the second x value, and then 3/2 and then 2. The right endpoints each time. So this means plugging them into our function values, which if you get your function, plug these in, plugging them in here, 4.75, 4, 2.75, 1, add them up, multiply, and we get that this area is approximately 6.25. Now let's talk about this as an estimation. What kind of estimation is this? Well, looking at the picture, we can tell that this is leaving out some area that we were supposed to include, so this is an underestimation. But I want you to explain it this way. We know this is going to be an underestimation even if we don't see a picture because the function is decreasing, so the right side of the rectangle is always going to be lower than where the left side would be if we took the left side up to the curve. So we will say that this underestimates the actual area because this function f of x is decreasing. And we're using right endpoints. The last part of that isn't really necessary because we were told to use right endpoints. The reason that it's giving us an underestimation is because f of x decreases. Now let's find the actual area. So using the limit process to find the area of the region. So let's start with writing down our formula. So remember what the actual area is. The limit as we take amount of rectangles to infinity, or we increase them without bound, of the sum from the first rectangle to the nth rectangle, the last one, of the area of each rectangle. And the area is the width, delta x, times the height, f of c sub I. So if this is the formula that we're using, we have to know what each of these parts are. So let's start by finding the area, which is finding the width and the height. So remember the width, b minus a over n, but this time n is not 4 rectangles. N is going to be taken to an infinite amount of rectangles. So we're going to write that delta x, which is b minus a over n. B and a are still from our interval here, so 2 minus 0 over n, or 2 over n. N, remember, is going to be approaching infinity. We don't have a definite value for it yet. Then our c sub I. C sub I, the x value that we plug into our function value to find the height, is a plus I times delta x. The a is the starting value from the interval, that's 0, plus I times our delta x value is 2 over n. Simplify this because we can. 2I over n is our c sub I. Now we're going to plug this into our function to get the height, width times height for area. So if the function is negative x squared plus 5, this is going to be negative of 2I over n squared plus 5. We want to simplify this. So simplifying this, we get negative 4I squared over n squared plus 5. Now we're going to take these pieces and plug them in to our formula here. So we've got the width goes in the delta x. We've got the f of c sub I goes in for our height, f of c sub I. Let's rewrite with what we have now. The limit as n increases without bound, the sum from I equals 1 to n, delta x 2 over n times negative 4I squared over n squared plus 5. Now here's where knowing our formulas and our shortcuts is really valuable so that we don't waste time doing too much in here, more work than we have to, and it makes it a simpler sum. So one thing to know is the I, that's the thing that's changing in this summation. So this is the only variable that's in this expression. And remember the sum properties, one of the sum properties is that, and I'm going to back up so you can see that slide again, we can take out any constant multiple, anything that doesn't have a variable in it. This has a variable in it, the I, so the I stays inside because it's the variable. But the K is a constant multiple, it can get pulled out. So that means 2 over n is a constant multiple. It can get pulled out of the sum. Now the limit is still going to be in the front there, but this is being pulled out of the sum. So let's rewrite what this looks like. The limit as n approaches infinity, 2 over n times the sum from 1 to n of negative 4I squared over n squared plus 5. Now let's use another one of our properties. We have the sum of a sum. We can break up this sum. Here's what I mean. That's a lot of sums there, but here's what I mean. The sum from 1 to n of 4I squared over n squared with the negative, and the sum from 1 to n of 5. So that's how we mean by breaking it up. After breaking it up, I've got another constant multiple right here that can come out of just that sum. So let's see what that looks like now. Limit 2 over n is out of both of them, but the negative 4 over n squared, sum from 1 to n of I squared, plus the sum from 1 to n of 5. Okay, so now looking back at our formulas, we've got the sum of I squared. We know that formula, and we know the formula for the sum of a constant. So let's replace those with what we know. And I don't want to get confused with what we did here. This was our part B. So I'm going to section this off, and we may need more space. And let's label this is our part C that we're doing. So we're rewriting our expression, the limit as n approaches infinity of 2 over n, negative 4 over n squared. Now all of this part, we're going to use our formula for what the sum of I squared is. That's our n plus 1, 2n plus 1, all over 6, plus the sum of 5 from 1 to n. Well, that's, remember, the constant times the upper limit. We have n of those 5s. Okay, so I use my formulas there. Now it just takes some simplifying and remembering our limit properties, because now all we have left is a limit. We got rid of our sum by using those properties. So let's do some simplifying, such as we have a factor of n. We can cancel one of those out. 4 goes into 6. 2 goes into both 4 and 6, so we've got 2/3 left there. And that's possibly about it for right there. Let's go ahead now and distribute this to both this term and to this term and see what we have left. So again, I'm going to write limit because I haven't taken a limit yet. I don't want to forget that I have to. Distributing the 2 over n to the first group makes 2 times 2, or 2 times negative 2, so that's negative 4 times n plus 1 times 2n plus 1, n times 3, so that's 3n squared. And the distributed to the 5n makes 2 times 5n is 10n over n. Now, the n's cancel from that term. And again, we don't want to have to do more work than we need to, especially in a long problem like this. So let's talk about what we have without having to do too much here. If I were to FOIL this expression out completely, I've got an n times a 2n, and that's going to give me my biggest exponent of n squared. So we're going to have n times 2n is 2n squared, then times negative 4 makes negative 8n squared, and everything that comes after that is not as big as n squared. So I'm going to say plus dot dot dot, because even though we can multiply those and figure those out, it's going to be insignificant, because remember, when we're taking the limit at infinity, we're using our degree shortcuts. So I'm just looking for the degree of the top and the bottom, or the highest exponent. So what comes after n squared is insignificant. So that's from that first fraction. From the other fraction, I still have plus 10. So using my degree shortcuts, I've got leading coefficients, because the degrees are the same, n squared, leading coefficients gives me negative 8/3 plus the limit of 10, no matter where n is going, is 10. Add those up and we get 7 1/3, unless you want to call it 22/3. And there's our exact area. Compare it to the estimation that we did in part B. We said this estimation was supposed to be an underestimation, and it is. This is under the actual area. Not by much, but it is slightly under. Make sure you also watch the next video for the perspective on a function of y.